Hi students, and welcome to this last part of number systems, that is the part 4. In this lecture we are going to study about some of the very important properties of real numbers. Then we are going to look at the method how to find the square root of any number using geometry and how exactly to represent the square root of any number on the number line. Then further we are going to study some of the basic identities involving the square roots, and last but not the least we are going to study some of the very important properties of positive and negative exponents of real numbers. So let's quickly begin this lecture. Before we begin this lecture, let's recall some of the very important points regarding real numbers, rational numbers and the irrational numbers. So real numbers are the numbers that consist of rational numbers plus irrational numbers. So all the irrational numbers together with the rational numbers constitute the set of real numbers. Now let's see about the rational numbers. The sum, difference, product and division of two rational numbers is always a rational number. So if we have got two rational numbers and if we add them or we subtract them, if we multiply them or if we divide them, the final result would always be a rational number. The second is, rational numbers satisfy the closure property under addition, subtraction, multiplication and division. So rational numbers always satisfy the closure property under the operation of addition, subtraction, multiplication or division. Let's see some of the points about irrational numbers. The sum, difference, multiplication and division of irrational numbers are not always irrational. So we cannot tell it for sure whether if we add two irrational numbers or subtract them or multiply them or divide them, the final result would be an irrational number or a rational number. It actually depends on the value of the two irrational numbers. Irrational numbers do not satisfy the closure property under addition, subtraction, multiplication and division. So irrational numbers do not satisfy this closure property under the operation of addition, subtraction, multiplication and division. Now let's see some of the properties of real numbers. The first is commutative law, and in that let's see the commutative law of addition. This is nothing but a plus b equal to b plus a. So if we have got two real numbers a and b, then a plus b would be equal to b plus a. So it doesn't matter if we change the sequence. That is, if b takes the place of a and a takes the place of b, the result remains the same. So this is known as commutative law of addition. For example, if we consider the case of 5 plus 1 by 2, your 5 is a real number and 1 by 2 is also a real number. So 5 plus 1 by 2 would be equal to 1 by 2 plus 5, and that's always true, because if we add these two numbers we get the answer as 11 by 2, and if we add these two numbers we get the answer as 11 by 2. Therefore commutative law of addition holds for real numbers. The next is commutative law of multiplication. So if we have got two real numbers a and b, then a into b would be equal to b into a. Again, if we change the order, that is b takes the place of a and a takes the place of b, then the product remains the same. For example, if we consider a equal to be 5 and b equal to 1 by 2, then 5 into 1 by 2 would be equal to 1 by 2 into 5, and this is always true because both these yield the same result, that is 5 by 2. Therefore the commutative law of multiplication holds for real numbers. Now let's see about the associative law. So in that again we have the addition law, and it says that a plus b plus c is equal to a plus bracket of b plus c. So if we add these two terms a plus b and then add a third term, this is equal to first term plus the addition of last two terms. So actually what we have done here is we have taken the operation of addition for these two numbers a and b first, and then we have added the result to the third number c. This is actually equal to, if we add the second and the third term first and then add this result to the first number, actually here the sequence is changed. That is, first and second terms are being added first and then being added to the third term. But here the second and third term are being added first and the result is added to the first term. So let's try to understand it through an example. If we take the value of a to be 2, value of b to be 4 and the value of c to be 5, then 2 plus 4 plus 5 would be equal to 2 plus 4 plus 5. and actually if you look at this LHS term, then the result is 11, and even the RHS yields the same result, that is equal to 11. Therefore, the associative law of addition holds for real numbers. Similarly, let's look at the multiplication law. It says that A cross bracket B cross C is equal to bracket of A cross B cross C. Again, this is the same as associative law of addition, just that instead of a plus sign, there's a multiplication sign. So again, let's look at an example. 2 cross 3 cross 2 by 3 would be equal to 2 cross 3 cross 2 by 3. Now, if we look at the LHS, this 3 and this 3 gets cancelled, and what we get finally is 2 cross 2, which is equal to 4. And here, if we see the result, we get 2 cross 3, which is 6, into 2 by 3 would be equal to 4. Thus, LHS is equal to RHS, and all are equal to 4. Therefore, the associative law of multiplication holds for real numbers. The next is the distributive law. This law says that if we have got 3 numbers A, B, C, then A cross of B plus C would be equal to A cross B plus A cross C. So what we observe here is this term is taken with this term along with this sign, plus this term is taken with this term along with this operator. Therefore, A cross of B plus C would be equal to A cross B plus is here plus A cross C. So what actually has been done is we have split this operation into 2 parts, A cross B plus A cross C. So again, let's look at an example. If we consider 3 numbers, A equal to be 3, B equal to 1 by 3, and C equal to 1 by 6, then A cross of B plus C would be 3 cross 1 by 3 plus 1 by 6. Similarly, this side would be equal to 3 cross 1 by 3, as B is equal to 1 by 3, plus 3 cross 1 by 6. Now here, if we see 1 by 3 plus 1 by 6 is equal to 1 by 2. So what we get here is 3 into 1 by 2. And from here, 3 and 3 gets cancelled, we get 1. And here, what we get is 1 by 2. So LHS is equal to 3 by 2, and RHS is also equal to 3 by 2. And so we can say that the distributive law holds for all the real numbers. Now, the square root of any positive real number exists, and that can also be represented on the number line. So if we take out the square root of any positive real number, then this square root is also represented on the number line. That is, this square root is also a real number, and that's quite obvious. The sum or difference of a rational number and an irrational number is an irrational number. This result we have already seen in the second lecture, where the sum or difference of a rational number with an irrational number is always an irrational number. Similarly, the product or division of a rational number with an irrational number is an irrational number. So the important thing is, the square root of any positive real number is also a real number and can be represented on the number line. The sum or difference and also the product or division of a rational number with an irrational number is always an irrational number. Now let's see some of the basic identities involving the square roots. So the first is under root of A into B is equal to under root of A into under root of B. So simply what we can do is, if we have under root sign inside A into B, AB is the product of 2 numbers A and B, then this could be written as the product of 2 numbers under root of A into under root of B. So we can split this term AB into 2 parts, A and B, and we can write this as under root of A into under root of B. Under root of A by B could be written as equal to under root of A divided by under root of B. So we can put the under root sign over both these numbers. The third is, if we multiply the 2 numbers under root A plus under root B into under root of A minus under root of B, then this product is equal to A minus B. Here what we can do is, we can use the formula, that is A square minus B square is equal to A minus B into A plus B, and when we apply this formula we get the result as A minus B. The fourth is under root of A plus under root of B whole square is equal to A plus B plus 2 times under root of AB. Now why is this so? If we expand this term, we get under root of A whole square plus under root of B whole square plus 2 times under root of A into under root of B. So from that we get the result as A plus B plus 2 times under root of AB. The next is under root of a plus under root of b into under root of c plus under root of d is equal to under root of ac plus under root of ad plus under root of bc plus under root of bd. This we get simply when we multiply these two terms. And the sixth property is a plus under root of b into a minus under root of b is equal to a square minus b. Again, here what we have done is we have used the formula that a square minus b square is equal to a minus b into a plus b. So when we apply this, we directly get this result, that is a square minus b. So these were some of the very basic identities involving the square roots. So let's try to solve an example. Check whether 4 root 5 comma 6 pi root 5 comma root 3 plus 19 comma pi minus 1 are irrational numbers or not. So in this problem, what we have to do is, we have been given 4 numbers, 4 root 5, 6 pi root 5, root 3 plus 19, pi minus 1. And we have to check whether these numbers are irrational numbers or they are rational numbers. So let's check out the solution of this. We know that root 5 is equal to 2.236, root 3 is equal to 1.732 and pi is equal to 3.1415 and so on. These are non-terminating and non-recurring decimals. Now let's check out the value of the first number, that is 4 root 5. Now 4 root 5 is equal to 4 into the value of this is 2.236. So we use this value to get the answer as 8.944 and so on. Now we clearly see that this number is non-terminating and non-recurring. Therefore this number would also be an irrational number. So this number is an irrational number. The second is 6 pi root 5. Now what we do is, we again use the value of root 5, that is 2.236. Therefore the answer would be 6 divided by 2.236, and this comes out to be equal to 2.68336 and so on. Again, this is a non-terminating and a non-recurring decimal. Therefore this is also an irrational number. The third number is root 3 plus 19. Now the value of root 3 is 1.732. Therefore we use this value to get the answer as 1.732 plus 19, which is equal to 20.732 and so on. Again, this is a non-terminating and non-recurring decimal. Therefore this is also an irrational number. And finally the fourth number is pi minus 1. The value of pi is 3.1415 and so on. Therefore we use this value to get the answer as 2.1415 and it goes on continuously. Therefore this is also a non-terminating and a non-recurring decimal. Thus this is also an irrational number. So all the 4 numbers, that is 4 root 5, 6 pi root 5, root 3 plus 19 and pi minus 1 are irrational numbers. Now why all these numbers are irrational numbers? We have earlier seen the property that if we add or subtract, multiply or divide any rational number with an irrational number, the result is always an irrational number. So without even multiplying or dividing or adding or subtracting these numbers, we could have got the result directly. The addition, subtraction, multiplication or division of a rational number with an irrational number is always an irrational number. Let's try to solve one more example. Find the value of, first part is 3 root 7 plus 2 root 5 minus 6 root 7 plus 8 root 5. And part B is under root of 7 minus under root of 3 whole square. So in this problem we have to find the values of 3 root 7 plus 2 root 5 minus 6 root 7 plus 8 root 5, and the second part is under root of 7 minus under root of 3 whole square. So now first of all we are going to solve the first part, and that is we have to find the value of 3 root 7 plus 2 root 5 minus 6 root 7 plus 8 root 5. Now we clearly see that there are 2 terms which have root 7 and there are 2 terms which have root 5. So we combine this term with this term and also this term with this term. So now when we add these 2 numbers, 3 root 7 minus 6 root 7, what we get is minus 3 root 7, and when we add these 2 numbers we get the answer as 10 root 5. Therefore the final result is minus 3 root 7 plus 10 root 5. So what we do is we pick out the terms having the same irrational numbers. So in this case it was root 7 and root 5. So we combine this term with this term and this term with this term, and we add them or subtract them as the case arises. For this the final value comes out to be minus 3 root 7 plus 10 root 5. Now let's solve the second part, which is we have to find the value of root 7 minus root 3 whole square. For this problem, we are going to apply the formula, which is a minus b whole square is equal to a square plus b square minus 2ab. Therefore, when we apply this formula, we get root 7 whole square plus root 3 whole square minus 2 times under root of 7 into under root of 3. Now, under root of 7 into under root of 3 is equal to under root of 21. Therefore, we get this value as minus 2 times under root of 21. Now, this is nothing but equal to 7 and this is nothing but equal to 3. Now, when we further solve them, we get the value as 7 plus 3 minus 2 root 21. Now, 7 plus 3 is equal to 10. Therefore, the answer is 10 minus 2 root 21. Therefore, the value of root 7 minus root 3 whole square is equal to 10 minus 2 root 21. Thus, we have solved this problem. Now, the next topic is finding square root of a real number using geometry. So, we are going to use the tool of geometry how to find out the exact value of square root of a real number. For that, we are going to take an example. Find the value of under root of 2.8. Now, 2.8 is a real number and we have to find out the square root of 2.8, and that too using geometry. So, let's look at the procedure for this. First of all, we draw a segment AB with length of 2.8. Therefore, in the first step, what we do is we draw a line segment AB of length 2.8. Here we have to calculate the value of under root of 2.8. So, what we do is we draw a line segment of length 2.8. Let us say that this point is A and this point is B. Now, in the next step, we draw a line segment BC of length 1 unit. So, from B, we draw a line segment BC of length 1 unit. Now, in the next step, what we do is we take the midpoint of AC. So, AC is also a line segment and we take the midpoint of AC to be O. Now, what we do is we take AO or OC as a radius and cut an arc this way. So, taking OA or OC, because both are equal to each other, as radius, we cut an arc keeping O as center. Now, in the next step, what we do is we draw a perpendicular from B such that it intersects the arc at the point T. Now, BD is a perpendicular to AC from the point B such that it cuts the arc at the point D. Now, join OD. Therefore, this segment BD comes out to be equal to under root of 2.8. Measure the length of BD and this is actually the value of under root of 2.8. Once again, let's see the procedure. In the first step, we draw the segment AB of length 2.8. Then from the point P, again we draw a segment of length 1 unit. Then we take the midpoint of AC to be O, and with O as center and radius as AO or OC, we draw an arc. Then in the next step, from the point B, we draw a perpendicular cutting the arc at the point D. So, join OD. Thus, the length of BD is actually equal to the value of under root of 2.8. Now, we have seen the procedure. But what's exactly the logic behind this? Why the value of BD is always the value which we want? There's a very simple logic behind this, and let's try to understand this. Let us take the number as root x, and so what we do is we draw AB of length x units, and this is exactly what we have done. Next, what we do is we draw a segment BC of length 1 unit. Now, in the next step, what we do is we take O as the center of AC, and from O we draw an arc this way such that the radius of this arc is AO or OC. Now, from the point P, we drop a perpendicular such that it intersects the curve at the point T. Join OD, and the length of BD is equal to under root of x. But how? Let's see. OC is equal to OD is equal to OA because all of them are equal to the radius of this arc, and this would be equal to x plus 1 divided by 2. Why? Because this entire length AC is equal to x plus 1, and this being the midpoint, therefore AO would be equal to OC would be equal to x plus 1 by 2. Therefore, the length of the radius of this arc is equal to x plus 1 divided by 2. Now, if we consider OB, then OB would be nothing but equal to x minus x plus 1 divided by 2. Why? Because this entire length AB is equal to x and the length of AO is equal to x plus 1 divided by 2. Therefore this length OB would be equal to x minus x plus 1 by 2, and this comes out to be equal to x minus 1 divided by 2. Therefore the length of OP is equal to x minus 1 divided by 2. Now BD square is equal to OD square minus OB square. Why? Because this is a right angle triangle, and in a right angle triangle we can use the Pythagoras theorem, and the Pythagoras theorem for this triangle would be OD square is equal to BD square plus OB square. Therefore BD square would be equal to OD square minus OB square. Now the value of OD is equal to x plus 1 divided by 2, and the value of OB is equal to x minus 1 divided by 2. Therefore this would be equal to x plus 1 whole square divided by 2 square minus x minus 1 whole square divided by 2 square. From this we get the value of BD square equal to 4x by 4, which is equal to x. Therefore the value of BD square is equal to x, and thus we get the result as BD equal to root x. So this is the very simple logic behind the length of BD being equal to root x. Now how to represent root x on the number line? So if we have to represent root x on the number line, then how to do that? In the earlier section we have seen how to calculate the value of root x. Now let's see how to actually represent root x on the number line. Now what we do is we simply do the same construction, that AB is equal to x, this length is equal to 1 units, and we draw an arc, and then BD would be the value of root x. Now taking B as the center and BD as a radius. Once again, taking B as the center and BD as the radius, we draw an arc, and let us say that this arc intersects this axis at the point E. Now if we say that this point B represents the 0 of the number line, then this segment BE is equal to root x, and so this point would represent root x on the number line. So once again what we have done is we have done the same construction, but then we took B as the center and BD as the radius, and we intercepted an arc. Let this arc intersects this axis at the point E. Now if we take B to be the 0 of the number line, then this segment BE would be equal to root x in length, and thus E would represent the number root x. Now let's try to understand the rationalization process. Now this is a very important operation which we do on the irrational numbers. But now what exactly is rationalization? Let's try to understand this. This is a process of converting the denominator containing square root sign into a form where the denominator is free of square root. So in this process what we do is we convert the denominator of any number containing the square root sign into a form where the denominator is free of square root sign. So this is actually conversion of a denominator containing square root into a form in which denominator does not contain the square root sign. But now what exactly do we do here? Here we multiply the numerator and the denominator by an irrational number which is called as the rationalization factor. In this method what exactly we do is we multiply the numerator and denominator by the same irrational number, and this number is known as the rationalization factor. So now let's try to understand this rationalization process through an example. Consider the expression 7 minus 3 root 3 divided by 2 minus root 3. So now this is the expression that 7 minus 3 root 3 divided by 2 minus root 3. Now this is an irrational number. Now we see that the denominator is 2 minus root 3. Now this is an irrational number, and this number contains the root sign. Therefore 3 has the root sign over here. Now let's see how we actually do the rationalization of this expression. We multiply the numerator and the denominator by 2 plus root 3. So here the rationalization factor is 2 plus root 3. So we are going to multiply the numerator and the denominator by 2 plus root 3. Now why is the rationalization factor 2 plus root 3? This is because we take the conjugate of this number. We have a minus sign over here, so we take a plus sign over here, and thus these two are conjugate of each other. Therefore we take 2 plus root 3 as the rationalization factor for this expression. Now let's see what exactly happens after rationalization. 7 minus 3 root 3 divided by 2 minus root 3 into 2 plus root 3 divided by 2 plus root 3. We multiply the numerator and denominator by the same rationalization factor. Now when we multiply the numerator and the denominator, what we get is the numerator becomes 14 plus 7 root 3 minus 6 root 3 minus 9, and the denominator becomes 4 minus 3. Here we simply use the formula a square minus b square equal to a minus b into a plus b. Therefore, this would be equal to 4 minus 3, and the denominator is nothing but equal to 1. And in the numerator we get the expression as 5 plus root 3 divided by 1. Thus we see that we have converted this expression which had denominator with a square root sign into a form where the denominator is free of square root sign. Here we have converted the denominator from irrational number to a rational number. So let's try to solve an example. Given that root 5 is equal to 2.236 approximately, find to 3 places of decimal the value of 7 by root 5. So in this problem we have been given the value of root 5 equal to 2.236 approximately, and we have to find to 3 places of decimal the value of 7 by root 5. So let's see how to solve this problem. The rationalization factor is equal to root 5. Now we have to find the value of 7 by root 5. The denominator is root 5, and we have to convert this root 5 into a rational number. So now what we do is we simply multiply and divide by root 5. Therefore 7 by root 5 could be written as equal to 7 into root 5 divided by root 5 into root 5. Now root 5 into root 5 is nothing but equal to 5, and therefore this becomes equal to 7 by 5 into root 5. Now the value of 7 by 5 is equal to 1.4, and the value of root 5 is given to be 2.236. Now when we multiply 1.4 into 2.236, we get the final answer as 3.1304. Therefore the value of 7 by root 5 is equal to 3.1304. Here we could have directly found the value of 7 by root 5 by dividing 7 by 2.236. But what we have done is we have simply rationalized this number into a form whose value could be easily calculated. Here we just had to multiply these two numbers, and if we won't have done the rationalization, then we have to divide 7 by 2.236. Dividing a number by 2.236 is a lengthy and a difficult task, but if we have to multiply, it's very easy. So the method of rationalization actually reduces the expression to a very simple form. So let's try to see one more example. Evaluate the value of root 5 minus 2 divided by root 5 plus 2 minus root 5 plus 2 divided by root 5 minus 2. So in this problem we have to evaluate the value of root 5 minus 2 divided by root 5 plus 2, this is a one expression, minus root 5 plus 2 divided by root 5 minus 2, this is also an expression. We have to find the value of this combined expression. So the expression could be written as root 5 minus 2 divided by root 5 plus 2 minus root 5 plus 2 divided by root 5 minus 2. Now if we look at this expression, the denominator is root 5 plus 2. Therefore the rationalization factor for this expression should be root 5 minus 2, because we take the conjugate of the denominator. Similarly, if we look at this expression, then the denominator is root 5 minus 2. Now the conjugate of root 5 minus 2 is root 5 plus 2. And now we rationalize this expression and we rationalize this expression. Therefore this would be equal to root 5 minus 2 divided by root 5 plus 2 into root 5 minus 2 divided by root 5 minus 2 minus of root 5 plus 2 divided by root 5 minus 2 into root 5 plus 2 divided by root 5 plus 2. Now root 5 plus 2 into root 5 minus 2 would be equal to 5 minus 4, and so this would be equal to root 5 minus 2 whole square, because this is nothing but equal to root 5 minus 2 whole square. The denominator we get 5 minus 4 minus this would be equal to root 5 plus 2 whole square divided by 5 minus 4, and so this is equal to root 5 minus 2 whole square minus root 5 plus 2 whole square. Thus this becomes equal to root 5 minus 2 whole square minus root 5 plus 2 whole square. Now when we expand this, we get 5 plus 4 minus 4 root 5 minus 5 minus 4 minus 4 root 5. Now simply use the formula of a minus b whole square and a plus b whole square to get this expression. Now 5 and 5 gets cancelled, 4 and 4 gets cancelled, and when we add these two irrational terms, what we get the final answer as minus 8 root 5. Thus the final value of root 5 minus 2 divided by root 5 plus 2 minus root 5 plus 2 divided by root 5 minus 2 is equal to minus 8 root 5. Now this is a very simple answer in comparison to this expression. So using the rationalization process, we can convert a very lengthy expression of irrational numbers into a very simple expression. So that is why the tool of rationalization is so widely used when solving problems on irrational numbers. Now let's try to understand the integral exponents of a real number. This is something we are going to study now. First is positive exponent. So for any real number a and a positive integer n, we can define a to the power of n, or the exponent of a being n, as a to the power of n equal to a into a into a into a and so on n times. So we multiply a n times to get the value of a to the power of n. So a to the power of n is nothing but equal to a multiplied by a n times. So this number a is known as the base and n is known as the exponent. So for any real number a and a positive integer n, we define a to the power of n as equal to a into a into a and so on up to n times. Your a is called as the base and n is called as the exponent. So let's understand this through examples. The value of 2 to the power of 4 is equal to 2 into 2 into 2 into 2 4 times, and this is equal to 16. So the base is 2 and the exponent is 4. So what we do is we multiply 2 by 2 up to 4 times, and so the final value is equal to 16. Similarly, 2 by 3 to the power of 2, or the exponent being 2, is equal to 2 by 3 into 2 by 3. Here we multiply 2 by 3 2 times. So 2 by 3 into 2 by 3 is equal to 4 by 9. Similarly, if we take the number minus 1 by 3 whole cube, then this is equal to minus 1 by 3 into minus 1 by 3 into minus 1 by 3, and this is equal to minus 1 by 27. So whenever we say a to the power of n, it means that a is being multiplied n times. Now let's take the case for negative exponent. Earlier we have seen the case of positive exponent. Let's see about the negative exponent. For any non-zero real number a and a positive integer n, a to the power of minus n is equal to 1 by a to the power of n, and this is equal to 1 by a into a into a and so on up to n times. So this is actually minus n, as n is a positive integer, therefore minus n would be a negative integer. So a to the power of negative exponent is equal to 1 by a to the power of n. Now we know the value of a to the power of n as equal to a into a into a and so on up to n times. Therefore whenever we have any number and its exponent is negative, then what we do is simply we write it as 1 by a to the power of n, and then we know the value of a to the power of n, we can apply it, and this way we get the value of a to the power of minus n. So for example, 2 to the power of minus 4. Now again 4 is a positive integer and minus 4 would be a negative. So here the exponent is minus 4, base is 2. Therefore this is written as 1 by 2 to the power of 4, and 2 to the power of 4 is equal to 2 into 2 into 2 into 2 and so on up to 4 times. Thus this value is equal to 1 by 16. Similarly, the value of 2 by 3 to the power of minus 2 is equal to, we write 1 by 2 by 3, but this is nothing but equal to 3 by 2, and which is equal to 3 by 2 into 3 by 2, and this is equal to 9 by 4. Similarly, minus 1 by 3 to the power of minus 3 is equal to minus 3 by 1 into minus 3 by 1 into minus 3 by 1, and that is equal to minus 20. So this is how we solve for negative exponents. One very important point is, if we have 0 as the exponent, then a to the power of 0 is equal to 1. Thus whenever the exponent of any real number is equal to 0, then this is equal to 1. So one by one we are going to see some of the very important laws of integral exponents. So the first law states that if a is any real number and m and n are positive integers, then a to the power of m into a to the power of n is equal to a to the power of m plus n. So if we have any two numbers such that it is a to the power of m and a to the power of n, and if they are being multiplied, then the final result is a to the power of m plus n. So we can write this as equal to a to the power of m plus n. Let's see an example. 5 square into 5 to the power of 5. So if we have to multiply 5 square into 5 to the power of 5, this could be written as equal to 5 to the power of 2 plus 5, which is equal to 5 to the power of 7. So 5 square into 5 to the power of 5 is nothing but equal to 5 to the power of 7. We simply add these indices or exponents. So we can say that if we have to multiply a to the power of m with a to the power of n, then their product is nothing but equal to a to the power of m plus n. We simply add the exponents. The second law says that if a is a non-zero real number and m and n are positive integers, then a to the power of m divided by a to the power of n is equal to a to the power of m minus n. So here simply if we have to divide a to the power of m by a to the power of n, this is equal to a to the power of m minus n. In the case of multiplication, the exponents were being added. Now in the case of division, the exponents are subtracted. So a to the power of m by a to the power of n is equal to a to the power of m minus n. So for example, 3 cube when divided by 3 square is equal to 3 to the power of 3 minus 2, and this is equal to 3 to the power of 1, which is equal to 3. Thus if we have to divide 3 cube by 3 square, we can simply write it as 3 to the power of 3 minus 2. We subtract both these exponents to get the final value as equal to 3. Thus if we have to divide two numbers, a to the power of m and a to the power of n, then this is equal to a to the power of m minus n. Let's see the third law of exponents. If a is any real number and m and n are positive integers, then a to the power of m whole to the power of n is equal to a to the power of m into n, which is equal to a to the power of n whole to the power of m. So if we have a as any real number and m and n are positive integers, then a to the power of m whole to the power of n is equal to a to the power of m into n. We simply multiply both these exponents, and this could also be written as a to the power of n to the power of m. For example, if we have the number 2 cubed to the power of 4, now this could be written as 2 to the power of 3 into 4, which is equal to 2 to the power of 12. Now this could also be written as 2 to the power of 4 whole cube. Thus we have used this property and we get the final result as 2 to the power of 12. Similarly, if we take the case as 5 squared to the power of 3, then this is equal to 5 to the power of 2 into 3. We simply multiply both these exponents, and this is equal to 5 to the power of 6. Now again this could be written as equal to 5 cube whole square. So we take the square of 5 cube. Thus a to the power of m whole to the power of n is equal to a to the power of m into n, which is also equal to a to the power of n whole to the power of m. The fourth law says that if a and b are real numbers and m and n are positive integers, then ab to the power of n is equal to a to the power of n into b to the power of n. So this is one of the very important result. If we have any two numbers ab and we have to take the exponent as n to the product of this two numbers ab, then they could be individually written as a to the power of n into b to the power of n. Similarly, if we have a by b whole to the power of n, then this could be written as a to the power of n divided by b to the power of n. So the fourth law of exponent says that if a and b are real numbers and m and n are positive integers, then ab to the power of n could be written as a to the power of n into b to the power of n. And similarly, if we have a by b to the power of n, then this could be written as a to the power of n divided by b to the power of n. So let's try to solve an example based on the above concept. Evaluate each of the following. First, a part is 3 to the power of 45 into 3 to the power of 55 minus 3 to the power of 23 into 3 to the power of 77, and b part is 1 by 2 to the power of 4 into minus 3 by 4 to the power of 2 into 16 by 27 whole square. So we have to evaluate the value of these two parts a and b. Now let's look at the first part, which is 3 to the power of 45 into 3 to the power of 55 minus 3 to the power of 23 into 3 to the power of 77. So now they can be clubbed as one part and they can be clubbed as one part. So 3 to the power of 45 into 3 to the power of 55 minus 3 to the power of 23 into 3 to the power of 77. Now we know that a to the power of m into a to the power of n is equal to a to the power of m plus n. We simply add the exponents. So this would be equal to 3 to the power of 45 plus 55, and this would be equal to 3 to the power of 23 plus 77. Now 45 plus 55 is 100, and also 23 plus 77 is equal to 100. So this equals to 3 to the power of 100 minus 3 to the power of 100, and thus the final answer is equal to 0. Let's solve the second part. The second part is 1 by 2 to the power of 4 into minus 3 by 4 to the power of 2 into 16 by 27 to the power of 2. Now this could be further written as 1 into minus 3 square into 16 square divided by 2 to the power of 4 into 4 square into 27 square. Here we have used one of the properties of the exponent and written this expression as this way. Now this is equal to 1 into 3 square into, this could be written as 4 square whole square divided by 2 to the power of 4 into 4 square into 3 cube whole square. Now this is 4 square to the power of 2, and this is 4 square. From this we get answer as 4 square, which is equal to 16, and from here what we get is 3 to the power of 4. Now this could be further reduced to 1 into 16 divided by 2 to the power of 4 into 3 to the power of 4. Now also 2 to the power of 4 is nothing but equal to 16. So 16 and 16 gets cancelled, and what we get is 1 by 3 to the power of 4. Now 3 to the power of 4 is nothing but equal to 81, and thus the final answer would be 1 by 81. So the final value of this expression is 1 by 81. So simply using the laws of exponents, we can find the answer to this problem. Now earlier we have seen the laws of integral exponents. Now it's time for us to see the laws of rational exponents. So the first is a to the power of m into a to the power of n is equal to a to the power of m plus n. So this is the same as the integral one. A to the power of m divided by a to the power of n is equal to a to the power of m minus n. This is also the same as the integral exponents. The third is a to the power of m whole to the power of n is equal to a to the power of m into n. This is also the same as the integral one. The next is a to the power of minus n is equal to 1 by a to the power of n. So whenever we have minus n, we write it as 1 by a to the power of n. And this is also the same as the integral one. The next is a to the power of m by n is equal to a to the power of m whole to the power of 1 by n. Now this is equal to a to the power of 1 by n whole to the power of m. We can actually interchange the powers, this we know. That is, we can write a to the power of m by n equal to the nth root of a to the power of m. So this is actually called as the nth root, and this could be further written as the nth root of a to the power of m. Now m by n could be written as m into 1 by n. We can write this as a to the power of m whole to the power of 1 by n, and again these two powers can be interchanged. Now a to the power of m by n is nothing but equal to the nth root of a to the power of n, and this could be written as the nth root of a to the power of m. The sixth is ab to the power of m is equal to a to the power of m into b to the power of m. So this is also the same as the integral exponents. And the seventh is a by b to the power of m is equal to a to the power of m divided by b to the power of m. Now this is also the same as integral exponents. Now the important point here is a and b are positive real numbers, and m and n are rational numbers. That's why we are looking at the laws of rational exponents. Your a and b are positive real numbers. We have taken them to be positive real numbers, and the exponents m and n are rational numbers. So these are some of the laws of rational exponents, which are almost similar to the laws of integral exponents. So it's time for us to solve a few examples based on rational exponents. Simplify the fifth root of 243 to the power of minus 3, and the part B is we have to simplify the expression third root of the fourth root of x to the power of 5. So the first is the fifth root of 243 to the power of minus 3. Now this could be written as 243 to the power of minus 3 by 5. This is the law of rational exponents. That is, if we have a fifth root, so we can write this power as 1 by 5, and thus this could be further written as 243 to the power of minus 3 by 5. The 243 could be written as equal to 3 to the power of 5. So this expression becomes 3 to the power of 5 whole to the power of minus 3 by 5. Now these two could be multiplied together. and thus 5 and 5 gets cancelled, and what we get is 3 to the power of minus 3. Now 3 to the power of minus 3 is nothing but equal to 1 by 3 to the power of 3, and which is equal to 1 by 27. Thus the final value of fifth root of 243 to the power of minus 3 is equal to 1 by 27. Let's look at the b part. Now the b part is the third root of the fourth root of x to the power of 5. Now this expression is nothing but equal to x to the power of 5 by 4, as the fourth root could be written as equal to 1 by 4, and what we get is third root of x to the power of 5 by 4. Now again this could be further simplified as x to the power of 5 by 4 whole to the power of 1 by 3, because the third root could be written as equal to 1 by 3. Thus we multiply these two powers together to get the final answer as x to the power of 5 by 12. Thus the final value of this expression is equal to x to the power of 5 by 12. Thus, using the laws of exponents, we can reduce very lengthy terms to very simplified expressions. Now let's start to solve the last problem, and this problem says that solve for x, and we have been given the equation as 7 to the power of x minus 2 into 11 to the power of 3x minus 11 equal to 539. So we have to solve this equation and find the value of x. Now how to do that? Let's look at the solution of this. We have been given the equation as 7 to the power of x minus 2 into 11 to the power of 3x minus 11 equal to 539. Now what we do is we factorize this 539 into its factors to get 49 into 11, and this 49 could be written as 7 square. Therefore 7 to the power of x minus 2 into 11 to the power of 3x minus 11 is equal to 7 square into 11. Now what we do next is we equate the exponents, because this term would generate this term and this term would generate this term. Thus when we equate the exponents, we get x minus 2 equal to 2 and 3x minus 11 equal to 1. From this we get x equal to 4, and from this we get the value of x equal to 4 as well. So x equal to 4 is the final answer. Thus the value of x obtained from this equation is equal to 4. So using the laws of exponents, we have solved this problem. So that was end of our chapter on number systems. So in a nutshell, let's try to summarize all the important concepts that we have learned in this chapter. A number r is called a rational number if it can be written in the form of p by q, where p and q are integers and q is not equal to 0. So any number r is a rational number if it can be expressed in the form of p by q, where p and q are integers and q is not equal to 0. The second is a number s is called an irrational number if it cannot be expressed in the form of p by q, where p and q are integers and q is not equal to 0. So any number which cannot be expressed in the form of p by q is known as a rational number. The third point is the decimal expansion of a rational number is either terminating or non-terminating recurring. Fourth, the decimal expansion of an irrational number is non-terminating and non-recurring. Moreover, a number whose decimal expansion is non-terminating, non-recurring is called as an irrational number. So any number whose decimal expansion is non-terminating and non-recurring is called an irrational number. All the rational and irrational numbers make up the collection of real numbers. So if we add all the rational numbers and add all the irrational numbers, then they together constitute the set of real numbers. The sixth is there is unique real number corresponding to every point on the number line. Also corresponding to each real number, there is a unique point on the number line. So there is always a unique real number corresponding to every point on the number line, and every real number could be uniquely represented on the number line. The seventh is if r is rational and s is irrational, then r plus s and r minus s are irrational numbers. Also r into s and r by s are also irrational numbers, where r is not equal to 0. So if r and s are two irrational numbers, then their sum, their product, their difference and their division is always an irrational number. If n is a natural number other than a perfect square, then root n is an irrational number. So this was all about the number systems, and I really hope that you have enjoyed learning this chapter.